Okay, so I realized I wasn't going to get to my last slide, so I thought I'd show it to you now. So we get rid of the time pressure. So this just summarizes some very recent results over the last year or two that have been established using the methods I'm discussing. So let me just briefly explain three results. One is a result that I got with Ian Agol and Bill Thurston. We had this series of results about the complexity of various problems in low dimensional topology, and what was missing was an NP-complete problem. So it turns out there is a natural problem in low dimensional topology that is NP-complete, and that is the problem of computing the genus of a knot in a three-dimensional compact manifold. So the genus of a knot is just the ordinary genus of a surface whose boundary is that knot. It's the smallest genus that you can find among surfaces that bound the knot. So whenever you have a curve that bounds some surface, you can define its genus to be that number. And computing that genus, or asking whether that genus is smaller than an integer g, turns out to be NP-complete. Now, there's thousands of NP-complete problems. What makes this interesting is it sort of ties in the complexity of geometry problems of this type into these other classes. So we now have some idea of how to compare the difficulty of some problems in topology to problems in other fields. Another recent result, which Jeff Lagarius and Bill Thurston, is sort of interesting because the statement of the result is purely a result in differential geometry. It has seemingly nothing to do with complexity or algorithms. But the proof goes through these ideas of normal surface theory and algorithms and bounding running time of algorithms. And the result is that if you have a curve in R3 now, an unknotted curve, so maybe a curve like that winds around a lot, it's unknotted, so it bounds some disk. The question is, given the length of the curve, what can you say about the area of the disk? That's called isoperimetric inequality. And of course, these are very classical for curves in the plane. But in this setting, nothing was known about the relationship between the area of these embedded disks and the length of the curve. And we managed, using these ideas, to get both upper and lower bounds. So it turns out that the area of some unknotting disk is always smaller or equal to a constant times the length over r squared times the length squared. Now this exponent, length over r, involves a quantity called the thickness of the knot, which measures the size of a neighborhood. If you made the knot out of rope, r would be the radius of the rope. And you also get a lower bound, which is roughly of the same order, except the exponent is linear instead of squared. So this is sort of interesting as a result in differential geometry that's obtained by these methods. And finally, there were some results in the last couple of years by Simon King and independently by Mijatovic, which are sort of interesting. They looked at the following question, also obtained by time of results I'll be talking about. They looked at the problem of, supposing you had a triangulation of a three-sphere, how far is it from a polytopic triangulation? So the boundary, how far is it from a triangulation obtained by taking the boundary of some convex polyhedra? And the kind of moves you allow to get from one triangulation to another are these sometimes called bistellar moves, or sometimes Packner moves. And it doesn't matter which ones you use. So you allow things like subdivision of I've drawn it in 2 dimensions, where a triangle is divided into 3. 2 adjacent triangles can be retriangulated in that way by changing the diagonal. There's corresponding moves in 3 dimensions. There's 3-dimensional subdivision and replacing 2 tetrahedra by 3. So how many moves do you need to get from one triangulation to another if you start with n tetrahedra, or 3 simplices, and they showed that you never need more, that there's some universal constant C1 so that the number is never more than C1 to the n squared. And King also obtained the lower bound. He found examples where the number needed was greater or equal to C2 to the n. So you need exponentially many moves in 3 dimensions. Something. In a sense, you could use this for a recognition algorithm, but it uses the old one. So it's not really, it uses the techniques of the 3-sphere recognition. But that's right, a corollary of this would be 3-sphere recognition, because you could check all possible moves and see if you get the 3-sphere, and there's a bound on how many moves you need to check if you start with some triangulated object. Okay, so that's just a little advertisement for the effectiveness of these techniques. But now we'll go back for a while to discussing the way that normal surfaces are used in algorithms. So last time we defined normal surfaces and saw how there's only finitely many disjoint ones in a triangulated manifold, and how that was used to establish the Kneser finiteness of the connect sum of 3 manifolds, a basic result in 3-manifold topology. That was back in the 20s that Kneser did that. And a big next step was the connection of normal surfaces to algorithms, which was done by Haken. So Haken noticed that that these normal surfaces can be defined algebraically. So far we've just done geometry. But now we're going to connect these to actually to linear programming. So to do that, we noticed that there's 4 types of triangles and 3 types of quadrilateral up to deformation in every tetrahedron. And we can completely determine a normal surface just by counting how many of each of these things there are. So for example, in a particular tetrahedron that's shown here, there's 4 triangles of this type, 2 of this type, and 1 of that type. There's no triangles near that vertex, and there's no quadrilaterals. So we can keep track of these numbers in a vector. You'll have 7 coordinates for each tetrahedron, 4 representing the 4 triangles and 3 representing the 3 quadrilaterals. And this T tetrahedron, the triangulation, so there's 7 T entries in this vector altogether. So for example, a vector representing a normal surface that intersects a tetrahedron in this picture might have these 7 coordinates in it somewhere. There's a 4 here indicating 4 triangles, a 2 here indicating 2 triangles, a 0 indicating 0 triangles there, 1 indicating 1 triangle, and these 3 zeros indicating no tetrahedra. So we've got a vector with positive or non-negative integer entries. Here's what it looks like for a surface, for a curve in a surface. There you'll have only 3T. You get 3 types of edges in every triangle, and you'll get a vector with 3T entries. Even in the, before I get to this side, I should point out that even in the case of curves on surfaces, this is sort of interesting. It gives you an incredibly efficient way of representing a curve, if you think about it. You know, for example, supposing you were drawing curves with a graphics routine, the standard way of representing a curve would be to put a series of vertices down and connect them up. So you'd have an ordered list of vertices representing a curve. If you do that, the number of the size of the data set you use is linear in the number of points. Well, if you represent a curve like this, then the size of the data set is logarithmic in the number of points. So it's a very efficient way of representing a curve. All right, well, so now you can represent a curve or a surface as an integer vector, and the thing to notice is there's a very simple condition that says which vector, if you just start with an integer vector with 70 coordinates or 3t coordinates in a surface, when does it represent a curve? Do all vectors with non-negative entries represent a curve or just some? And there's only one condition you need to check, a very simple condition, which you can see in this example here. When we have two adjacent triangles, we want to make sure that when we put them together, we don't have any loose edges. So if we take these two triangles and put them together, there's 4 arcs coming in from the left and 2 from the right. We have sort of leftover points here that aren't identified to anything, and then we're out of luck. We don't have a curve in the surface. We have sort of loose ends. But as long as the numbers are right, there's just exactly one way to put them together to get a closed curve with no boundary. And so there's a condition that says the number of curves coming from the left is equal to the number of curves coming from the right. Now if you look at the number of curves coming in from one side, there's 2 types of vector entries that have ends on this edge here. V24 and V23 in this case both contribute to the intersections with that edge. And there's 2 from the right. There's this type and this type as shown. So the condition for there being no loose boundary, no loose edges, is that Vi plus Vj equals Vk plus Vl. And the key point there is that you have a linear equation there. So we have integer vectors and linear equations representing our curves. And exactly the same thing is true in 3 dimensions. In order to have these pieces fit together without any loose boundary, you need to have matching along 2-dimensional faces that are glued together, like this one and this one. And it turns out, again, there's two types of elementary disk on the left and 2 types of elementary disk on the right that have a particular type of curve on this triangle. If you look on this triangle, what kind of elementary disk in here could give you this kind of edge? Well, it's either quadrilateral with one of its boundary edges here, or it's a triangle with one of its boundary edges there. And so if you count those types of disks and make sure they match up, you again get the same type of linear equations. Vi plus Vj equals Vk plus Vl. So normal surfaces exactly correspond to integer linear vectors. Integer vectors subject to these linear equations also have these inequalities. Vi is greater or equal to 0. That should be greater or equal to. And there's another technical condition which is irrelevant for us. It's important, but not necessary for for understanding the subject, so I'll ignore it. So we get these equations that a vector satisfies called the normal surface equations, and we now have an algebraic description of a surface as an integer vector. So this is nice, but not that useful in itself. What makes this so useful is that the algebra of vectors has a nice correspondence to the geometry of surfaces. So this is a rather amazing coincidence when you think about it, but it works out really nicely. So I've illustrated this here for curves. Here what we have is 2 different normal surfaces. So this arc here represents part of a normal curve called B, and this curve here represents part of a normal curve called A. And these 2 curves happen to intersect one another. Each one itself is embedded, but these 2 embedded objects intersect, they cross there. And they each have normal vectors, these integer vectors, and we can add those normal vectors. And it turns out that adding those normal vectors, it's quite easy to see, gives you a new vector, and that new vector, of course, by the linearity of those normal surface equations, also satisfies the equations, and so also gives you a normal curve. And there's a geometric way of getting from these 2 intersecting surfaces to this sum surface, and it's called regular exchange. You just do a geometric operation where you split the curves open along the intersection points and reparameterize them so that it looks like this. there's only one way to do this. There's actually two ways to reparameterize, but there's only one way that gives a normal curve. The other way gives a curve that doubles back along one of the edges at least. So we have a situation where algebra is reflected in the geometry. There's a one-to-one correspondence between the addition of vectors and the geometric sum of surfaces. Here's what geometric sum looks like in 3 dimensions. We have 2 intersecting surfaces here, and they intersect along an arc this time in this tetrahedra. And we've simply flipped over these little triangles. We've exchanged them. That's called regular exchange. And we have a new surface which is still normal, consists of 2 triangular disjoint now triangles, 2 elementary triangles. And that gives a new normal surface which corresponds to the sum of those 2 vectors. So this is it turns out to be a very natural operation. All sorts of things are preserved by this addition or behave naturally. For example, the Euler characteristic adds. The Euler characteristic of V plus the Euler characteristic of W is the Euler characteristic of the surface associated with the sum. So you take 2 normal surfaces that may intersect one another, V and W. You add them together. You do this geometric sum operation where wherever they intersect, you do this kind of thing. And you get a new surface, and its Euler characteristic will just be the sum of the old Euler characteristic. And that's because, easy to see, because this process doesn't change the number of edges or vertices or faces, and so when you compute the Euler characteristic, nothing changes. And other things also act naturally under this sum. For example, the weight, the number of times that these surfaces intersect the edges, that doesn't change when you do this process. So the weight of V plus the weight of W is the weight of V plus W. Remember that in the framework we're thinking in, weight is like area concentrated along the edges. So we have a way of adding the areas of surfaces. It's something that you can't do in differential geometry. Okay, well, once we can add these vectors, it's natural to try and do integer linear programming. So Haken did this. You want to look at some sort of basis for all these integer vectors. And you do that by looking for what Haken called fundamental surfaces. So a surface is fundamental if it can't be written as a sum of 2 other surfaces. And it's easy to see that when you start with a vector with positive integer entries, you can write it as a plus b only a finite number of times before you arrive at a fundamental vector. But not so easy to see is that there's only finitely many fundamental vectors or fundamental surfaces. That's well known now, but it wasn't so well known when Haken was doing this. But that's more or less a standard fact now in integer linear programming. So we wind up with this finite collection of fundamental surfaces satisfying the normal equations. And that's the key to algorithms. We now have a finite collection of surfaces that we can test for various properties. If we can show that this fundamental collection is sufficiently broad to include useful surfaces. So I'm going to show you now how this works for a specific example, namely the unknotting problem. So we'll go quickly through the unknotting algorithm that Haken gave. How do you decide whether a knot is trivial or not? We've now done all the work we need to do this algorithm. This was question? This was solved by this algorithm was given by Haken in 1961. There were many attempts to do it over the preceding 40 years, so it was one of the central problems of topology at that time. So how does it work? Well, the first thing you do is you make everything piecewise linear. So you start with a knot like this, some kind of picture like that, then it's not too hard to make everything PL. You triangulate the knot, you triangulate a ball containing the knot in its one skeleton. There's some interesting issues, which I'm going to skip, about how many triangles you need to do this. Those are related to complexity questions on the running time of this kind of algorithm. And I'll skip those now. So the first step after you've triangulated everything is to notice that if K is unknotted, then it's the boundary of some disk. That's the right point of view. This isn't the point of view that many other people had taken. Some people had tried to solve this problem by looking at the knot group, trying to solve the word problem for this special class of groups that arise. Some people had tried to find some moves that reduce a curve like this to the trivial curve, Reiter-Meister moves or generalizations of them. But it turned out that the right point of view is to think of this as a three-dimensional problem, not a problem about graphs in the plane, and look for a disk that has boundary this curve. So any unknot has a spanning disk. It's not so obvious sometimes what it is because they wind around and over and back. They're quite hard to see once the curve gets complicated. But that's the point of view to take. Look for an unknotting disk. Now, if everything's triangulated and K bounds a disk, then it's the boundary for normal disk. That's step 2. So let's go through that argument quickly. So remember we showed last time that if you took any surface at all, then by a process of moving around the surface, an isotopy, just deforming the surface, and some compressions where you squeeze off disks lying in the complement of the surface, by those two processes you could simplify the intersections with tetrahedra until you got a normal surface. So what would happen in our case? We start with a knot that bounds some complicated disk drawn in red here. And if you push it around by an isotopy, that's not changing the fact that it bounds a disk. You get some new disks. That's not a problem. And then the second process of compression, what does that do in our setting here? That can sometimes cause some problems. But when you compress a disk, when you compress a two-dimensional disk, so you take some curve that bounds a disk in the complement, and then you compress along that disk. All you do is you pop off a two-sphere, and you're left with a new disk that bounds the curve K. Okay, so that's not going to mess up the fact that you have an unknotting disk. You've just changed what that disk is. In fact, you've made it simpler in the sense of having maybe less area or smaller weight, which is the area of a normal disk. So by a series of compressions and isotopies, we arrive eventually at a normal disk that has boundary K. And now we can change the question of does K bound a disk to the question of does K bound a normal disk. Now, unfortunately, there could be infinitely many normal surfaces, so we haven't got an algorithm yet. Even though we've reduced the problem to this special class of surfaces, what we want to do is show that if K bounds a disk, then it bounds a fundamental disk, because there's only a fundamental normal disk, because there's only finitely many of those, and then we can actually look at them one by one. So supposing K bounds a disk, and this disk is not fundamental, then its vector, the vector representing it can be written as A plus B. This wouldn't be so good if neither of A and B were a disk. But it turns out whenever D equals A plus B and D is a disk, then one of A and B is also a disk. At least if we're a little careful about how we write D as A plus B. So here's an illustration of what could happen. Remember that Euler characteristics add, and the Euler characteristic of a disk D is just equal to 1. So one possibility is that the disk is equal to A plus B, where A is another disk and B is a torus. The Euler characteristics work out right. Another possibility might be that A is a punctured torus, a torus with boundary, and B is a two-sphere. There's various other possibilities, but this is a typical case that you analyze. There's about half a dozen cases to look at. What happens if D equals A plus B and A represents a disk and B a torus, like this? Then we can simply take a new disk A and throw away the old disk D and continue with our analysis. So we found a simpler disk that has boundary K. We just throw away this torus here and go from this rather big disk to the smaller disk A.
So the other thing, B, is always something without a boundary. The other thing that
Well, it is in this picture. Actually, you have to analyze the case, for example, that maybe one of these is a disk and one is an annulus. They could have intersecting boundary. I've completely slurred over what happens at the boundary, by the way, in this discussion. You know, I've only talked about closed surfaces and closed normal surfaces. These surfaces have boundary. That's just a technical point. There's no real difficulty handling the boundary, but I've just ignored it. But no, you have to look at the case where both A and B have boundary too, in those cases. But each case is easy to analyze. Let me just explain one more time what this picture means. There's some vector representing D, and you can write that vector as the sum of two other vectors, both of which have non-negative entries, and both of which satisfy these linear equations. So each of A and B corresponds to some surface. And when you take the geometric sum of A and B, which means whenever they intersect, you do this process of exchange that we saw a few minutes ago. When you do that process, here they intersect along one curve, which means you sort of change the way they are connected at that curve. When you do that, you'll get the surface D that we started with. That's what's going on here. And what this analysis shows, if you go through all of it, is that no matter what possibilities you have for A and B, you always have a situation where A is a disk of simpler weight whenever it's written as a sum.
So did you say how K is represented in terms of as an integer vector or linear system or something like that?
How the curve K?
How is K given in terms of?
Yeah. Okay. I wasn't going to say that, but I will since you asked. So really, what you do is you remove a neighborhood of the knot K and look at a manifold with boundary whose torus, which has boundary of torus. And then you ask, is there a disk in this 3 manifold whose boundary is on this torus? So that's how you do it. You don't care where it is on the boundary. You just say, is there a disk whose boundary is on the torus?
So that gives you a system of linear equations.
There's linear equations, right? You simply don't have these equations Vi plus Vj equals Vk plus Vl if you have a face that's on the boundary. It has no linear equations associated to it. But so that's how you specify it. You have the exact same type of system of equations.
So you don't know, of course, the Hilbert basis ahead of time. So you want to find somehow a Hilbert basis element and you don't know the full Hilbert basis. So that's find one.
Yeah. So it turns out that once you have the triangulation, you can explicitly calculate the Hilbert basis.
Is that what you do?
That's what we do. Yeah. Hawken just said this is a finite set and we can look at all of it. But in my work with Ligarius and Pippinger, we explicitly calculated the size of that set and which vectors were in it. Yeah. So I'll get to that in a second. So we've reduced the problem to asking, is there a disk which is fundamental, which is not equal to A plus B? And that kind of vector is called an element of the Hilbert basis. I won't take the time to explain how that basis is calculated, but the idea is there's some compact set in this set of solutions to these equations. There's some finite collection of integer solutions called the Hilbert basis, which are all the fundamental solutions. And you can explicitly, this is in z to the 7t, some subset of z to the 7t plus, z7t plus. So you can explicitly bound the integer coordinates of these points in order to see how many points you have to check. And there's some exponential number in t, which isn't too hard to calculate. And once you've got a bound on how many points you need to check, you just check each integer lattice point inside this set to see if it's a disk. If the curve is unknotted, then one of these points is a disk whose boundary lies on that knot. If the curve is knotted, then none of these points is a disk with boundary on the knot. And that's how the algorithm goes. You just look at each of these one by one. Now, how do you tell if one of these points represents a disk? Well, there's a very simple formula given that vector to calculate the Euler characteristic. And the disk is the only surface with boundary whose Euler characteristic is 1. So there's a very fast way of checking what the topology of one of these vectors is. Because each of these vectors is connected, it's a bunch of triangles glued together, and you can compute its Euler characteristic quite easily. Let me talk a little bit about the complexity bounds of this algorithm. So to get a complexity bound, you need to bound the size of these integer vectors that you look at. And what we showed there was that each coordinate of these vectors, these fundamental vectors that you need to check to see if it's a disk, each coordinate is bounded by t times 2 to the 7t plus 2. And that's gotten by looking at the special form of the linear equations that comprise this system of equations. So once you bound all the coordinates, you can just see how many integer lattice points there are, and there's at most this many fundamental surfaces, and that's how many you have to check to see if any is an unknotting disk. And so an algorithm for unknotting runs in time constant to the t squared. Actually, you can improve this by doing some more work, using some improvements to Hawkins algorithms that were found by Jaco. You can improve this to c1 to the t, or another constant to the n, where n was the number of crossings. T is the number of tetrahedra in a triangulation. That's a linear function of the number of crossings of the knot. So you can use either one as a measure of complexity. You can also push this a little further to show that the unknotting problem is in NP. For those of you who don't know what NP is, in a word, it just means that if I assert that a knot is the unknot, I can give a proof of it for an individual case in polynomial time and in the number of crossings. Like you can certify that a knot is trivial in polynomial time, if not determine it. So the key point there is the key problem there is that is the following. To give a certification or proof that a certain curve is unknotted, what you do is you triangulate everything, and then you present the normal surface coordinates of the unknotting disk. So actually finding this may take exponential time, but just presenting it can be done very quickly. And now somebody needs to take these equations, somebody needs to take these coordinates and check, does that represent an unknotting disk? Well, it's very easy, again, to see that this represents an Euler characteristic 1 surface with the right boundary. That computation is very fast. The hard part is to show that this represents a connected surface. You have to show that this doesn't represent some for example, a torus with a hole in it together with a two-sphere, the connectedness turns out to be the hardest part of this whole development. And originally we used some trick to show connectedness, but I'll skip that development. But we now have a polynomial time algorithm to determine connectedness. So that problem has disappeared, and then we get that the recognition of unknotting can be certified in polynomial time, which means it's an NP problem. Now, let me move on now. So that's that's the end of our course in normal surfaces. So I want to talk about some of these connections to differential geometry and minimal area surfaces. So let me tell you about a theorem from the 70s in differential geometry called the minimal Dane's lemma, and how in retrospect we see that maybe this is connected to what we just did. So the minimal Dane's lemma says the following. Supposing you take some Riemannian three-dimensional manifold with convex boundary. So you might think of an example as being a handle body like this. You take some metric on the handle body so that it's curving towards the inside of the boundary. This is not a very restrictive condition. Any three-manifold with boundary admits such a metric, so there's not a restriction at all. And now supposing you have a curve gamma on the boundary of this three-manifold, which is null homotopic. So that means you can push it down to a point inside this three-manifold. Then the conclusion of this lemma is that, first of all, this curve bounds a disk of smallest area, D, and secondly, that this disk has no self-intersections. The least area disk doesn't cross itself at all. This is a very powerful assertion. The first assertion is analysis. There was a lot of analysis over many years. This is called Plateau's problem, to show that curves bound disks of least area. This is a very hard problem, but it was solved over the course of it was solved around the first result in Rn was given in the 30s, and then the result in general manifolds was given in the late 40s. So the existence of these least area disks was established. The real contribution here is that this disk doesn't cross itself. You know that this curve gamma is the boundary of some disk because it's null homotopic, but that disk might cross itself. It's not clear at all that there even is a disk that's embedded. This is not assuming the existence of an embedded disk. So the fact that any null homotopic curve on the boundary of a three-manifold bounds an embedded disk is a highly non-trivial result called Dane's lemma. Dane gave a proof of it in around 1920, which was incorrect. It was immediately recognized that it was an essential lemma that we needed to understand three manifolds. There were many attempts to fix it. It was finally proven correctly in 1957 by Papakyriakopoulos by a rather hard topological argument. Meeks and Yao showed that this least area disk is embedded. So it gave a new proof of Dane's lemma, which was actually stronger than Papakyriakopoulos' method, and turned out to be very useful in three-dimensional topology. It solved a good collection of open problems at the time, in particular having to do with group actions on manifolds, because least area surfaces behave nicely when they're translated around by a finite group. So in retrospect, this is closely connected with what we just did with Unknot recognition, in the sense that we could have taken this curve gamma that we used, and we could have looked for a least weight normal disk. And it turns out that if you think about it from this point of view, instead of a least area disk being embedded, we'd find that a least weight disk was embedded, and it had to be fundamental. And so in some sense, the Meek-Xiao lemma should have told us that by looking for least weight normal surfaces, we'll be able to find something interesting out about unknots. Okay, so now I want to talk about recognition problems that have been looked at recently. We talked about recognizing whether a curve is unknotted. About 10 years ago, there was a big breakthrough in perhaps the next most interesting problem after knotting for recognition, which is recognizing the three-sphere. So the question here was, if somebody gives you a three-manifold as a collection of simplices with faces identified, can you tell if it's the three-sphere or not? So these are old problems, recognition. You know, originally the two-sphere recognition problem was unknown. People didn't know if the world was a two-sphere. There's still some interesting work going on right now on what the topology of the universe is. Some of you may have heard about this. This is work that Jeff Weeks is doing with some cosmologists. The idea here is you look back 15 billion years and you see the cosmic background radiation, and by looking for repeating patterns in that, you try to determine if there's some topology in the universe. If there was some topology, you'd see the same thing from two different directions, roughly. And I understand from some inside information that the recent analysis shows that the Poincare homology sphere is the most likely candidate for the topology of the universe now. All right, so more concretely, though, let's talk about recognizing the three-sphere. How do these methods apply in this case? Novikov established that there is no procedure, no algorithm that will recognize the five-sphere. So it wasn't obvious at all that there even was a procedure possible for the three-sphere. But a procedure was given about 10 years ago. That's very beautiful. I want to try and explain it briefly. It was given by Rubinstein and Thomson. So I talked quite a bit about this with Rubinstein, and I know that his inspiration did come from this point of view, looking at minimal surfaces. I talk with Thomson too sometimes. Anyway, so let's take a minute to just say what a minimal surface is, since I never actually defined it. It's there's different definitions. One is a surface with mean curvature 0. So you can just take a point on this surface. There's two principal curvatures associated with curves passing through that point. If they average out to 0 at every point, then the surface is said to be minimal. Doesn't seem to have much to do with minimal, but it turns out that that's the condition that says that it's locally area minimizing. And you can sort of see that because if one of these curvatures was bigger than the other one, you could push in the direction of the greater curvature and decrease the area a little bit. They have to balance. You can think of a soap film. Both these curvatures are pulling on the film, and they have to balance for it to be in equilibrium. An equivalent definition is that if you take any point, some disk in the neighborhood of that point has least area for its boundary. And there's many other definitions based on analysis involving things like conformal harmonic mappings and the calculus of variations. Well, what can you do about the existence of these minimal surfaces? there's a couple of classical theorems that are sort of relevant to us. One is a theorem of Listernik and Schnurman from 1929. They showed that if you take a two-dimensional sphere with some metric on it, then no matter what the metric is, there's always three simple geodesics. So there's always three simple curves, simple closed curves, that are locally shortest for length. And in fact, for some surfaces, there's exactly three. For example, if you take an ellipsoid that's close to a sphere, close to a round sphere, but not quite, then Marston Morse showed that there's exactly three. But for other metrics, there's many, many simple geodesics. And we're actually going to distinguish between two types of geodesics, stable and unstable. We talked about this a little bit yesterday. Stable geodesics are not only locally but globally shortest. Unstable geodesics are locally shortest, but there's a way of pushing them off themselves so that their length decreases on a big scale. So here's an interesting fact that characterizes a two-dimensional sphere. With any metric at all on it, a two-sphere always has an unstable geodesics. Always has an unstable geodesic. Other surfaces may or may not have unstable geodesics. So here's a sort of illustration. I've drawn three different metrics on a two-sphere. In each case, you can find some unstable geodesic somewhere, often more than one. But other surfaces may or may not have any. So for example, this surface, genus 2 surface, has no unstable geodesics. If I take, say, a hyperbolic metric on it. And this surface of genus 2 does have an unstable geodesic. So there's a way of characterizing a two-sphere, which isn't the usual way that you might check whether a manifold is the two-sphere. But it turns out that following this line of thought is what leads to the recognition theorem. So why is it that you expect a two-sphere to have an unstable geodesic? How would you prove such a thing? This is more or less the idea of Listernik-Schnurman. What you do is you start with a family of curves, gamma t. So you start with gamma 0 and sweep out the whole two-sphere by a family of curves, starting and ending with a point. And what you do is then you shorten the family at the same time, all the curves in the family at the same time. So you pick some shortening procedure, of which there's quite a few, and you just shorten them all at the same time. And what happens is that the short curves on this end shrink down to a point on the left. The short curves on this end shrink down to a point on the right. But you can prove some continuity result that says that there must be some point in the middle where a curve gets stuck. And a curve that gets stuck converges to a geodesic. So let's use that observation to make a not very useful recognition algorithm for the two-sphere. Let's take a mystery surface F and ask, is our surface the two-sphere? So the procedure goes like this. First, we cut it along a maximal family of stable disjoint geodesics. If there aren't any, as in the standard two-spheres, all the geodesics are unstable, then we're not in. If there aren't any stable geodesics, then we have a two-sphere and we're done. Any other surface always has a stable geodesic. But we might be in trouble because we could have a two-sphere with a stable geodesic, so we're not quite done yet. We have to think, what do we do if our surface does have a stable geodesic, or several? Well, we cut open along those geodesics, and then we look at the pieces. Now, those pieces may have one or several boundary components. Let's just look at the case where there's one boundary component. Ignore the case where there's two boundary components, which didn't fit on the page. Anyway, if there's exactly one boundary component, then how can we tell whether it's a ball or some surface of other than a ball? It turns out that it's a ball if and only if it has an unstable geodesic. So if it's a ball, then the same kind of sweep out argument we just saw says you can take this boundary component, run it over that component, and shrink to a point. You form a family of curves sweeping out that ball, and if you shorten that family, you'll wind up with an unstable geodesic. So balls have unstable geodesics. If it's a non-ball, it can't have an unstable geodesic. Why not? Well, if there was an unstable geodesic here, then you could push it further in, reducing the area, and you'd wind up with another stable geodesic inside. But we assume that there weren't any more stable geodesics. We already cut open along all the stable geodesics. So very briefly, that's the idea. Same thing works for 3 spheres. There's a corresponding theorem in differential geometry, which was proven by a series of people, that on given any metric on the 3-dimensional sphere, there's always an embedded minimal 2-sphere. So there's always some 2-sphere that looks like the equator of the standard 2-sphere, no matter what the Riemannian metric is. In fact, there's always 4 of these 2 spheres. And the theorem is proved more or less the same way. You run out a family of 2 spheres sweeping out the 3-sphere. You shorten them all together and show that an unstable surface hangs up in the middle. Because it's the technical details are much harder in 3 dimensions. So it's a lot of hard analysis that goes into that. And we can use that as the basis of a 3-sphere recognition theorem. We start with a mystery manifold M. We cut it up along stable minimal 2 spheres, as many as we can find.
How do you know that there are maximum?
How do we know that there aren't infinitely many?
Yeah, or no, how do you know that you've got all?
Or how do we actually find them and see that we get all? We'll see shortly. Yeah. Of course, the answer is you can't do it for minimal surfaces. That's why this isn't really an algorithm but it's a characterization. When we go to normal surfaces for minimal surfaces, we will be able to just look in the fundamental surfaces to see that we've got all of them. But we couldn't do it in this smooth setting, at least not directly. So we cut open along these minimal 2 spheres, and now we want to characterize the complementary pieces. So let's suppose we have a piece that just has a single boundary component. We want to ask, is this part of a 3-sphere or not? If it's part of a 3-sphere, it has to be a ball, an ordinary 3-ball up to homeomorphism. If it's not part of a if any piece is not part of a 3-sphere, then it's not a ball, then this is not part of a 3-sphere. So the key part of this argument turns out to be asking, is this piece a 3-ball or not a 3-ball? That's the hard part of this whole recognition problem. And it turns out that it's a 3-ball if and only if it contains an unstable minimal 2-sphere. A 3-ball, you start with this stable guy, you push it in and increase its area. Somewhere in the middle there's a unstable minimal 2-sphere, and then it can shrink down to a point on the other side. If you have some topology on the inside, then you won't have this unstable minimal 2-sphere inside. So why is it a B3? Let's look at this problem. Why is it a B3 if it has an unstable minimal 2-sphere? Well, you take that unstable minimal 2-sphere, you can push it off to either side and decrease the area a little bit. Once the area has started to decrease, you can keep pushing it until one of 2 things happens. Either it gets caught on the boundary or it shrinks down to a point. Well, it's not too hard to prove that if you have a manifold that's swept out by 2 spheres like this, then it's a 3-ball. So easy to believe, and it's not hard to prove. So there's a way of checking whether a manifold's a ball or not, and therefore whether it's a sphere or not. Does sweeping it out by, well, are these pieces free of unstable surfaces or not? So if we could just answer this question, we could find an algorithm to recognize the 3-sphere. Of course, we can't really find all the stable and unstable 2 spheres, but we can in the PL setting, where they're known as normal surfaces. We can certainly find the stable ones, the normal surfaces. We need to find what we mean by an unstable minimal surface in the piecewise linear setting. And that was a new idea introduced by Rubinstein. He defined what he calls almost normal surfaces. So whereas normal surfaces only had triangles and quadrilaterals in any tetrahedra, an almost normal surface allows one extra type of piece, which is this shown here. It's a sort of an octagonal piece. That's wasn't a super successful picture. Let me put another picture up here. These octagonal pieces of disk, which are allowed in exactly one tetrahedron. It's going to be normal in every other tetrahedron, but in one tetrahedron you're allowed to have this octagon. And this octagon, it's not so easy to see maybe from this picture, but this octagon has this octagonal disk has a property similar to an equatorial 2-sphere. Namely, you can push it off in 2 different directions in a unique way. In each direction there's one way to push it off to reduce its area. In this case, the area is the weight, the intersection with the edges. So you can see if I take this little red disk here and push this octagon across that's like this little disk here. If I push this octagon across this black disk here, I'll remove 2 points of intersection with the edges. That's a reduction of weight. So it turns out that these are the analog of unstable minimal surface or unstable minimal 2-sphere. And that was a real insight to see that this was the right way to make an unstable minimal 2-sphere in the normal surface setting. So now let's go through some of the highlights of the recognition algorithm. You first find the maximal family of normal 2 spheres. Then you want to check whether the complementary pieces are balls. So there's 2 types of complementary pieces. Some have more than one boundary components and some have only one boundary component. It turns out that the pieces with more than one boundary components are always balls with some holes removed. So here's a picture of a ball with some holes removed. Here's a pictorial representation where we have this guy with 2-sphere boundary components. How do you see? So this is sort of an amazing fact, actually. It's almost trivial to prove when you do it, but it's a sort of a very amazing fact. And the reason that these things have to be punctured balls, that these pieces with more than one boundary component are very easy to analyze, is that if you connect 2 of the 2 spheres together with a tube, and then try and shrink that 2-sphere that's the union of those 2, and you can always do that as long as there's at least 2, then you wind up eventually shrinking down to another boundary component because all the stable surfaces are at the boundary. And so you sweep out the entire manifold by 2 spheres, which shows that it's a punctured ball. And the other case is components with exactly one boundary component. And there again, we can show that it's a ball if and only it contains an unstable minimal 2-sphere, which in this case is an almost normal 2-sphere, a 2-sphere with exactly one of those octagon pieces in it. Now those octagon piece surfaces can be checked algorithmically by reducing it to a certain class of fundamental surfaces, just as in the unknotting problem. And I should say finally that the running time of this algorithm was analyzed by Casson, who showed essentially that it runs in time order of 3 to the t, where t is the number of tetrahedra. So I guess I'll stop there. Thanks.
the normal surface Hilbert basis?
In real life, you mean?
Yeah,
In
well,
an explicit.
and what software do you use?
There's actually a software package